So now I'm going to talk about potential functions and gradient vector fields. So I have a definition up here, a potential function, and usually we represent potential functions as phi of xy. That's what this Greek symbol is supposed to mean. Some people write phis like this. You can do it either way. It's the same phi that we used when we were talking about spherical coordinates. Anyway, our potential function phi is a multivariable function whose gradient vector field, capital F of xy, remember that whenever we talk about functions that have outputs that are vectors, we typically capitalize the function. It's given by the gradient of phi, which is equal to the partial derivative of phi with respect to x in the first component, the partial derivative with respect to y in the second component is equal to f. So maybe this looks like a lot of jargon, but really the concept is pretty straightforward. So let's say that I have a potential function, phi of xy is equal to, let's say, x squared y plus 3y. And notice that in order for it to be a potential function by definition, typically we talk about multivariable functions. So in this case I have a two-variable function, I have a variable x and a variable y, and my output is not a vector. I'll write that maybe in this other color, because we want this to be a real valued output. Potential functions always have real valued outputs. And now, if I have this as my potential function, I can find out what is the gradient vector field that's generated by this potential function. And the way that we do that is by taking the gradient of this. So when I take the gradient of phi of xy, recall that the gradient is the partial derivative of phi with respect to x. So I'm going to treat y as a constant. And for this term, the constant y is just going to be a coefficient, and I end up with 2xy, because the y comes along for the ride. This term goes to 0 because we're treating y as a constant. That's my first component function. My second component function, I'm taking the partial derivative of this with respect to y. So when I take the derivative of the first term with respect to y, I see that x squared is treated as my constant, so I'm left with just an x squared. And the derivative plus 3y with respect to y becomes 3. So this first component function, I'll write it out using our own notation, f1 of xy is equal to the partial derivative of my phi function with respect to x. And then my second component function, f2 of xy, is the partial derivative of my phi function with respect to y. Why is this interesting? Why is this helpful? Actually, it's really cool. And when we get to 16.3, we're going to talk about all sorts of properties that you get from gradient vector fields that you don't get from just any old vector field. But for now, we're just going to focus on some of the mechanics of what it is to be able to create gradient vector fields. Let's do another example. Hopefully this is a pretty straightforward computation. Let's say that our potential function, a real valued function that has inputs x, y, and outputs that's just some real number, not a vector. Our potential function phi is given by xy plus x minus y. And I want to know what is the gradient vector field associated with phi. And so in order to find my gradient vector field, I'm going to take the gradient of phi. And we know that the gradient is going to be the partial derivative with respect to x, which in this case is y plus 1 for the first component function. And then the partial derivative with respect to y, which in this case is x minus 1 for the second component function. So this is called capital F of xy, a vector function. It has an output that is vector, inputs that are points x, y. And this is what we call our gradient vector field. It's a gradient vector field because it's a vector field that's the gradient of a potential function. Now this is where the question gets interesting. Let's say that we didn't have our phi function. Maybe I'll pretend to black it out, but I want to keep it in mind for the work that we do in a little bit. So let's say if I didn't know what this was, and all I was given was the information that I have some function that I know is a gradient vector field, and my gradient vector field f of xy is equal to this. How could I work backwards to be able to figure out what this function is? And this is going to be our steps for working backwards. What do I mean by working backwards? I mean, given a gradient vector field, and typically we're going to call those capital F. Let's say we have this gradient vector field F. Find the potential function. And what do we call our potential function? Usually we call them phis, phi of xy. So asystematically, maybe I'll have you pause the video, think about it, what are the steps that you might do? How might you figure this out? So you paused the video and thought about it a little bit. You probably didn't pause the video. But we know that this function, our f function, is equal to the gradient of phi. So I can use the fact that the gradient of phi, I'll write this in one long line, is equal to the partial derivative of phi with respect to x in the first component and the partial derivative of phi with respect to y in the second component. And we see that that's equal to y plus 1 and x minus 1. So I can look at these first two terms, and I know that the partial derivative of phi with respect to x has to be equal to y plus 1. So I need to work backwards. Instead of taking the derivative, I'm going to anti-differentiate. So when I anti-differentiate, I'm going to make sure that I'm taking the antiderivative with respect to x. And I find out that this is my first guess, maybe I'll write guess, that phi sub 1 is equal to xy plus x. Because I took the antiderivative with respect to x, it means that each of these terms were constants, so I just put x's on as coefficients when I took my anti-differentiation. But notice that this phi function neglects the fact that it's close to the original, right? We're working backwards, we're trying to get to the original function, but we left out this y term. Why did we leave it out? It's because anytime you anti-differentiate, you need to make sure that you keep track of your constant, right? We know this from back in the day. Anti-differentiation, if I take the derivative of this function with respect to x, I get back here, and my constants just go to 0. But we have to be careful about what this constant is, because this constant could be some function of y, right? Because when we take our derivatives with respect to x, we're treating y as a constant. So we need to have some extra term here that's telling us that when I took my antiderivative with respect to x, I need to have some constant term that might include y. Similarly, so this gets us part of the way there. It gives us the first couple chunks. But we need to use more information, and we have more information over here. We have the fact that our partial derivative, of phi with respect to y is equal to x minus 1. So again, I'm going to anti-differentiate with respect to y. I can even write that out in notation. I'm going to take the integral of that side with respect to y, and I'm going to take the integral of this side with respect to y. And when I anti-differentiate with respect to y, I'm going to get some phi2 function. And this function, treating x and negative 1 as constants, I end up with xy minus y plus my constant. And my constant in this case is going to be a function of x. So now that I have this piece and I have this piece, I need to put these two pieces together to find out what my original function, my original potential function must be. And I see that any term that had both x's and y's in it is going to match between these two functions. That my xy term and my xy term match with one another, and it's because it's coming from this xy term. But any term in here that is only a function of x, that's going to be exactly this function of x. And any term that's just a function of y, that's going to be this function of y. And it means that my final phi function, maybe I can draw lines connecting those in red. I'll see that this x here is represented in this equation by this term. And this y here, the negative y actually, is represented by this term in this equation. So when I say putting these equations together, I mean some of the terms are going to match, and those are the ones that are in the original function. And the other terms are terms that are independent of the other variables. Let's see one more example now that we've formalized a system for thinking about this.